Hello and welcome. Let me discuss about random walk in 2D. We discuss about random walk on a square lattice. Let me give you an impression. Let me draw a square lattice or a square grid. That means it's a kind of, you can think it's a graph paper. So here it is, a square grid. It's a cartoon of a square grid. And the random walker is somewhere here. You can think this is the origin, okay? And the model is the walker can go in each time step, either in the positive direction, x direction, or in the negative x direction, or in the positive y direction, or in the negative y direction. So it can go to all its four nearest neighbor points. Okay, so this is our model at each time step. If I can separately draw, so here, suppose here is the particle or a walker, random walker. So the initial point is 0, 0. This is your x-axis. This is y-axis. And at each time step, it can go either in the right or left or up or down. So the right nearest neighbor would be 1, 0. This would be minus 1, 0. This would be 0, 1. And this would be 0, minus 1. All these four possibilities. Wherever it goes, suppose it comes here, suppose it comes here, okay? It can, from here, it can jump in either of the four directions, either these or that or these or this, okay? Each time step, it goes to one nearest neighbor points, okay? So the this way we create the random walk map, and we analyze the random walk map. Basically, we want to calculate the end-to-end distance, and we'll see how it goes with step. This is the simple what we'll do. Well, so let me go to the computer, but before I go to computer, let me tell you that if the initial position is x and y, okay, x and y, so x goes as x plus delta x, and y goes as y plus delta y at each time step, okay? And delta x and delta y can be plus minus 1. You see, this is delta x, this is delta y, this is delta x, this is delta y. They can be plus minus 1. So let me create this in computer with Python. Okay, so let me import from random. It's a random module in basic Python, core Python. From random, let me import choice. Choice is the function. It chooses from any of the arguments. Okay, so just some element, any element from any of the arguments. And of course, we need numpy as np, and to plot, we need matplot. Import matplotlib.pyplot as plot. All these three things we require. Okay, let me import them. These are the basic inputs. Oh, import matplotlib. Sorry, spelling mistake. Okay, okay. So let me now start from the some xy equal to 0, 0. So this is the starting point. Say, well, run it. Let me now write choice, choice, and inside in a list we give the choices. That means 1, 0, right, minus 1, 0, left, then 0, 1 up, and 0, minus 1 down. So these are the tuples, that means xy points. So basically these are delta x and delta y, okay, at each of its step. If I now run it, you get say 0, 1. It chooses 0, 1. If I run it again, it chooses another one, minus 1, 0, and so on. So, well, let me now write dx dy equal to this. What I am doing? I am unpacking this. It chooses one of them, and each of them is a tuple. So the first one goes to delta x, and the second one goes to delta y. So this is unpacking in Python, as we all know. Okay, now we have to update xy. It started from x0, 0. We have to update xy inside a loop. So for this, let me write a loop, for loop, for say time in range, say 5,000. Okay, and I have to indent this, and then I have to update x and y equal to x equal to b, x plus dx, and y would be y plus dy. Done. So at each time step, it chooses one of them and then updates x and y. Now I have to plot. And to plot in Matplotlib, we should create a list. So for that, let me create two empty lists first, x and y equal to this and this, two empty lists. These are capital X, capital Y. Okay, and the task is simple. Let me append them. So X goes to capital X list, and in capital Y, I append each Y. Okay, done. So it is, I'm sorry again. I'm doing the spelling mistake. Okay, so now this done. So the lists are done. That means one work is generated. Let me plot it. plt.plot. If I write capital X and capital Y, here you don't need to write plt.show because I am working in Jupyter notebook and Anaconda Jupyter notebook. So this is implied. So if I run it, so it will generate one work. Okay, this is one work of 5,000 steps. Okay, if I run it, if I start from again 0 and run this again and plot this again, you will get another. If I again start from 0, run these 5,000 steps again and plot them, so it is another work. So this way we can generate many works, and for statistical analysis we should take some kind of average on those things, and the physical quantity that we will actually calculate is the end-to-end distance. End-to-end distance means, suppose the worker started from here. I don't know where from it started. We should mark it while plotting. You can do that yourself. So suppose it started from this point and it goes zigzag, all this, and maybe it ends here, for example. So this to this distance is the end-to-end distance, and this is the Euclidean distance that we always calculate in geometry, plane geometry. Well, so this is how we generate work, and we should calculate now the end-to-end distance. Okay, to calculate those things, okay, let me write the entire thing, this entire thing inside a definition function. Okay, so let me first, it will be easy for me. Let me define a function called work, and I give the number of steps In this case, it was number steps equal to 5,000, but I can give anything. Okay, so this and x, every time it will start from 0, 0, so no problem. And for this time, we will not actually keep track of the capital X and capital Y lists, because we don't need the need to remember all the points. We only need to remember the end-to-end distance. At every time step, it proceeds somewhere at some place, and I need to calculate the distance from this point, from the initial point. Again, it goes to some place after some time, and we need to calculate the distances between the initial point and the final point. That way, we'll actually calculate the position of the particle or random walker at different time steps, right? So what I want to do is, let me write, say, POS equal to empty list. That means I will actually collect the positions in that. Okay, and like previous, I write for I in range, and this is steps. Okay, and then dx comma dy equal to choice. Inside that, I could copy that, but let me write it again so that you can pay attention. Okay, and 0, 1, 0, 1, and 0, minus 1. So this is the y, and let me write it x with xy equal to x plus dx and y plus dy. Okay, done. And let me calculate the np dot square root, then x star x plus y star y. So this is the Euclidean distance. That means x square plus y square and the square root of this. Since initial position is 0, 0, it is always x square plus y square. Otherwise, it would be x1 minus x2 whole square plus y1 minus y2 whole square under the square root, and so on. Okay, now I want to append this in the position POS. POS is the empty list where I keep track all those positions. POS dot append inside that. Okay, so my work is done. Now, since this is a Python function, I'll return the POS with position list. Okay, let me run it and check whether it is okay. Well, it is okay, no mistake. Okay, now I can write steps. Say step size is, say, 1,000. I can write. Okay, and this is for one walk. That means I want to create a walk of 1,000 steps. But if I want to create many walks, that means I have to repeat this. I have to use this function many times. So those are those different walks, these random walk maps would be different configurations. Okay, so let me write config equal to also 1,000. You can choose anything. Okay, I can write it in one line. Steps, comma, config equal to 1,000, comma 1,000. That means I want to create one random walk of 1,000 steps and 1,000 such random walks. Okay. So now I can call this walk. I can call this walk and steps. Oh, inside I can write as list comprehension. Let me call this walk and steps. Okay. So this way, one walk is generated, and how many times? For I in range. I is dummy variable, dummy index, no problem. I in range and config. Okay, so now this is a list comprehension. So I generate all those steps. Okay, let me name it as walks. Okay. Also, since I will be using the machinery of NumPy array, I should convert this list into a NumPy array. So it is better that I write np.array. So that will be, it is better. It will, the display will be better. The everything, all the other vectorization thing I can use later. So let me run it. Okay, it is running still because it is a star here. So done. So I have now created 1,000 random walks. Each walk is of 1,000 steps. Let me see how it looks. Walks. Oh, it looks rather clumsy because you see it is a 2D list. That means it is like a matrix. So the this is one walk. This is next walk. This is a one row, first row, second row, third row, and so on. Let me write it as for display. Let me write it as round walks, comma 2 for good display. Let me see how it shows. Okay, it is rather sober. Okay, so this is the first walk. This is the second walk. Third walk. Each row is the walk because I have created one row here and this row is repeated 1,000 times. So here it is a 1,000 by 1,000 2D array, or you can call it matrix. Okay, so you see for a single walk, it is for the first time step, next time step, next time step, next time step, and for the 1,000th time step. So you see the values are different. For the 1,000th time step, for the first walk, it was 27.2. For the 1,000th time step, for the second walk, it was 8.94. For some, it is 22.36, and so on. So the things are different. Well, now what I want to do is I want to take the average over all those configurations. That means I want to know the average position of a particle after one time step, two time step, three time step, and up to 1,000 time step. So what we do is that actually I have to, if you look at the first column, it is all the column members are for the first time step. All the second column members are for the second time step for different walks. This is one walk, this is second walk, this is third walk, and so on. Okay. So what we take is that we want to take the mean at each time step. That means I want to take the mean of the first column, mean of the second column, mean of the third column, and so on, so on. That means I want to take over all the different columns. Okay, and in Python NumPy, this is very easy. What we write, m work, okay, and equal to np dot mean, since every function and method in NumPy is vectorized and it can do operation on any dimensional n-dimensional arrays. So I can write walks, and then I can, if I write axis equal to 0, this is one very clever way of doing. And this, so axis 0 means I go from up down. This is up down. Up down is axis 0. If I go right left, then it is axis equal to 1. So if I write just axis equal to 0, that means it will take the first column and take the mean. It will take the second column and take the mean. Third column and take the mean. Let me run it. Done. Let me see what is m work is. Okay. So it is actually a 1D array. It should be on 1D array because this is the average of the first steps. This is the average of the many configurations at the second time step. This is the average of the many configurations, 1,000 configurations of the third time step, and so on. So this is how we have done. Okay, let me finish this. Okay, now I can plot plt.plot. If I write, say, Before that, I want to plot. I want to create the time array because time is here steps. So I can write t equal to range of steps. Okay, and I want to plot plt dot plot t versus m walk. So let me see that. Let me see that what is. So the plot is this. It will be soon evident that this is a power law with power less than 1. So it goes this way. If the power law would be with power law with power greater than 1, it would be this way. Okay. So it is evident. And with analytical result, we know that this m walk, that means the mean walk, the mean positions with time step, it goes actually as t to the power half. We actually know that let me r, if the r is the mean position, it goes as t to the power half in 1D and 2. So that means if we plot this r and t, it should be like this. Okay, t to the power half. So best way to see this, best way to check this is to take log and to find out whether this exponent is half or not. Well, so for that, let me actually write this for that because I will take log. So it will Python always starts from 0. So better I write 1 to steps plus 1. That means it will create time steps from 1 to steps. Okay. It doesn't matter. It doesn't matter because anyway it is the same. Where from you start, it is up to you. Okay. So now what I do is that I take the t equal to np dot log and t, and I take r equal to np dot log, and what we wrote here is m walk. So that means both are in log. Okay. Now if I write plt dot plot and t versus r, it should show as a straight line. So yeah, it is a straight line, but initial points are not good. Anyway, the law is only valid after some long time and so on. If I want to see with dotted things, the bullet symbols, it will be, yeah. I'm sorry. PLT dot plot, yeah, PLT dot plot. What is happening? No, log PLT dot plot should actually right. What happened? What happened? Oh no, something happened. Something happened. What happened? T equal to np dot log m walk. Let me check it again. M walk and m walk, and it's a log of this np dot log. M walk is this. M walk is this. Everything is all right. Did I do some mistake? Let me plot it again. T versus m walk. Okay, T versus m walk. Oh, I'm sorry. If I write T equal to np dot log. Oh, I did not actually. Did I do that? Yes. Np dot log of T and r equal to np dot log of m walk. Check it again. I called it m walk. Okay. So now done. Now plt dot plot T versus R. It should give a straight line. And if I write it as O, it should write it as O. That means with bullet symbols. Okay, so it's a fairly good straight line. If we measure the slope of the straight line, it should be close to half. Okay, so let me try to do that. For that, I import numpy dot polynomial. That means there is a numpy is a package. Under it, there is a polynomial is a module, and under that you have a sub module called polynomial again. So as poly. So it's a shortcut. And then I write poly dot polyfit. The function is polyfit. If I now put T versus R, T comma R, and if I write 1, that means since already we have taken log and it is a straight line, so it is a polyfit with polynomial of order 1. That means with a straight line. Y equal to mx plus c, kind of. Y equal to ax plus b or mx plus c, whatever way you write. Okay, so now this is polyfit. Okay, so let me do that. Did you see that we have got two coefficients? One is this, one is that. Actually, this is the way they write. This is the m, y equal to, if you write y equal to mx plus c, so this is the m, that means this is the slope, and this is the intercept. Okay. Ideally, it should be close to 0, but there are lots of errors, lots of not good values of good data points, because we need to average over many configurations, and we need to go for a very long long time. Okay, so anyway, so this is already very close to 0.5, which is the actual result. Okay, so I have to collect these two coefficients and find out the corrected values of R, and then we'll plot it. But before I do, let me actually discard some points, for example. Okay, so let me discard the first 20 points. This is, this is slicing. So we actually discarded 0 to 19 points, started from 20 until the end. Here also, I do 20, comma this. Let me run it again. But it's not very much improved. Not very much improved. We could actually discard many more points, maybe some 50 points or 100 points. We could discard. Yes, you see this value is closer to 0 now. Okay, so this way you can do lots of experimentation. Anyway, so this is a polyfit. Okay, you can, if you want, you can fit the entire data, but I have the choice of discarding the initial few points and so on. Anyway, so now you call polyhal, poly.polyhal. Okay, inside that you write the 100 colon, that means that many data, and well, before that I actually write COFFS equal to this. That means I collect this array of coefficients into this name. Okay, let me call it so as to use that. And now I write COEFFS. So that means it will take this data, T data, that means X data, and I will use these coefficients to calculate the fitted values of these R values. Okay, I call this R fit. I call this R fit. Okay, now let me run it again to make sure. So I calculate R fit. Okay, now I can plot plt dot plot the original data T versus R with bullet points, okay, and the PLT dot plot the 100 the sliced points and the RFID data, okay, and with line. Let me see how this plot looks like. So the you see the I have actually, since it's a log scale, the most of the data points are concentrated on the up scale here. You see the I have, since I have discarded these many hundred number of points. It's my wish. I mean, usually you can do that, and you have seen. You can see that this line, orange line, is the fitted line. Just to look it better, I can now, what I can do is that I can extend the data points. That means if I include this data point, one data point here, and join here, it should look like this. It look like better. Okay, let me see how it goes. You can do lots of things. You can actually write E extended, right? That you can write np dot insert E 100 this, and at 0 you put 0. Okay, so I want at the 0 position, that means the first position at 0. That means I want to draw the line from 0. Okay, you can do that, and the R extension, sorry, R extension, that is equal to np dot insert and RFID zero position, right? COEFFS 0. Okay, so for the time, I start from 0, but for the R at 0 position, that means here the data point will be coefficients at 0th coefficient. That means we have two coefficients here, 0 and 1. I mean, two coefficients. That means the intercept. That means the Y value. Okay, so this is the Y value. That means the intercept I add at this point. That means this point, wherever it will be, is corrected. Okay, and it will, the line will continue up to this. Well, this is nothing, just to show off. I mean, you do it in your own way. So like I write PLE dot plot. Okay, T versus R versus 0, and and PLT dot plot T extended extension, R extension, and a line, and a line. So not defined. TXT. Oh, I've not run it yet. I've not run it yet. So yeah, you see actually the line was up to here. Since I have included this point, the line is continued up to this. If I would plot this with, say, plus symbol, you see that you realize that actually the data points are here, these plus symbols, and one plus orange symbol is here. So it has actually this is a corrected value at 0 point by fitting. So this value, okay, and so this line is added. So this is this, but of course, for to begin with, you may not do all those things. You simply take T and R and just fit it to entire data. Okay, you can do that always. So first thing you do that, you polyfit with this, and then use polyval to calculate the fitted R values. You need not take the slice values. You can take the entire values. So that way you can do that. Okay, so thank you, and I end my lecture here.